Let's jump into a little stats fun with natural frequencies. So your father went to his doctor and was told that his test for a disease was positive. Now he is really worried and comes to ask you for help. After doing some reading, you find that for men of his age, the prevalence of the disease is 30% in the population, and the test that he had has a sensitivity of 50% and a specificity of 90%. He asks you, "Son, tell me what's the chance I have of this disease?" Okay, so try and do this in your head or on a napkin, whatever works for you. Now, if in the population we have 30% who have the disease, so this is the 100% of the population, we're going to have 30% that have the disease, 70% that don't have the disease. So far, easy. If your sensitivity is 50%, then 15 of the 30 will test positive. Makes sense, right? Now, if you have a specificity of 90%, remember the false positive rate is 10%, and therefore 7 of the 70 will also test positive. Falsely, but they will test positive. So that means 22 people test positive, of whom 15 have the disease. So the chance of disease is about, or is actually, 15 out of 22, which is about 70%. So who got that right? There must be a bunch of you at home with your hands up. Good for you. So let's try it again. A disease with a prevalence now of 4% must be diagnosed. The test has a sensitivity of 50% and a specificity of 90%. So same test. If the patient tests positive, what is the chance they have the disease? So we're going through this again. Out of the 100% of the population, 4 have the disease, 96 do not. With a sensitivity of 50%, 2 will test positive, and with a false positive rate of 10%, 9.6 will test positive who do not have the disease. So 11.6 people test positive, of whom 2 have the disease, so the chance of disease is 2 over 11.6, which is about 17%. So if you answered correctly, then you've done extremely well. A paper published in BMJ in 2003 published the results from a study which gave that exact problem to physicians with an average of 14 years experience, and the answers ranged from 1 to 99%, and half of them estimated the probability as 50%. Now remember those likelihood ratios that we talked about in a previous lecture? Well, they come in handy in diagnostic accuracy as well, because you can use them in situations with more than 2 test outcomes. So remember, for a binary test, no problem. But what if you have a test that has more than 2 levels or 2 outcomes? What do? Well, you can use likelihood ratios. So that's one of the big advantages. The other one that we're going to talk about is that there's a direct link from the pre-test probability to the post-test probability. And we just kind of went through an example of that, where it is important to know what the prevalence of the disease is in order to calculate the post-test probability. So though we've talked about likelihood ratios a fair amount so far, we may not have talked about how we express them in medicine. So a positive likelihood ratio can be expressed as how much more likely is a positive test to be found in a person with the disease than in a person without it. So how you calculate it is sensitivity divided by 1 minus specificity, which you'll remember is the false positive rate. Now, a negative likelihood ratio is how much more likely is a negative test to be found in a person without the condition or disease than a person with it. So the negative likelihood ratio is now 1 minus sensitivity over the specificity. Here's a slide that shows you the contingency table and how to calculate your positive likelihood ratio very quickly. We're looking at how much more often a positive test occurs in people with compared to those without the disease. As you know, as we just stated, the positive likelihood ratio is sensitivity divided by the false positive rate, or 1 minus specificity. Sensitivity, of course, is A over A plus C, and 1 minus specificity will be B over B plus D. What do likelihood ratios mean? Likelihood ratios can be considered diagnostic weights. With the probability of occurrence increasing, your ratio is going to go from 1, which, as you know, of a ratio, 1 means no diagnostic value. Just like the odds ratio or the relative risk, if you have an odds ratio or a relative risk of 1, it means no difference. So as your probability increases, your likelihood ratio is going to increase as well, from 1 all the way up to infinity, with likelihood ratios greater than 10 as considered a very strong positive test result. With the probability decreasing of occurrence decreasing, your likelihood ratio is going to decrease from 1 with no diagnostic value all the way to 0 and asymptotically approach 0, where a likelihood ratio of 0.1 is a strong negative test result. So this method of assessing the probability of an event occurring is based on Bayesian reasoning. So it's thanks to the Reverend Thomas Bayes, an English statistician from the 1700s, that we can take the pre-test probability and calculate the post-test probability. Now, in this case, the way the simplest way of doing this is you must have the pre-test odds, multiply it by the likelihood ratio of your test, and you get the post-test odds. Now, you'll remember odds and probabilities are not the same thing. In order to then convert your post-test odds to a post-test probability, the post-test probability is equal to the post-test odds divided by the post-test odds plus 1, and that gives you your post-test probability. Now, interestingly, if you don't have the pre-test odds and you only have the pre-test probability, which for instance could be the prevalence of the disease in your population, well, the pre-test odds is going to be equal to the pre-test probability divided by 1 minus the pre-test probability. Now you can see all that's quite convoluted. So what was developed was the Fagan nomogram, which does this for you. So you can see these three lines, these three vertical lines. You line up your pre-test probability as a percentage here. So you have 5%, okay? And then you say, okay, what's the likelihood ratio of the test? In this, for an example here, for appendicitis, you have the McBurney tenderness score and the test, and the likelihood ratio, positive likelihood ratio, is 3.4. So then you map out 3.4 here, and you draw a line between your 5% and your 3.4 here, straight through to the third line, which is your post-test probability, which is in this case 20%. Yay! So medical students used to run around with the Fagan nomogram and would be able to calculate the post-test probabilities this way. I'm certain none of you do that anymore because you just have your smartphone and it calculates it for you. But here we go. We've just explained to you how that calculation is done for you. So why have we not talked about the positive predictive value and the negative predictive value of a test? Well, because it depends on the accuracy of the test and on prevalence of the disease, whereas the likelihood ratio does not depend on the prevalence of the disease, and it gives you, through the ratio, an idea of strength of the test. So in that sense, you could assign it some utility that way. And that's the reason why it's best to work with the likelihood ratio than it is to try and express how good a test is through the positive predictive value, or negative predictive value for that matter. So in summary, when considering clinical decision making, all diagnostic studies share a similar structure, and you can appraise them in 3 steps. Are the results valid? Do I believe them? What are the results? For instance, what's the sensitivity, the specificity, the likelihood ratio? Can the test be used in our setting? And that's probably the important piece for the application of the test in your practice. And that brings us to the end of lecture 3 in part 4. Next up, in part 5, in the first lecture, we will talk more about statistical modeling.